What I have here is a mineral called Beryl. This is just a section of a large crystal about 1 meter long. Here's the cross section right here, and then if I rotate it around, you can see some of the striations here that are associated with the growth of this crystal. Now this is a very interesting mineral because it's made out of beryllium. It's a beryllium aluminum silicate where the silica tetrahedra are all linked together in a circle or a ring, and the beryllium and aluminum fit in between those rings. Now beryllium is a very rare element. You won't find it in most places. It's in trace amounts, but in here it's a major constituent. So how do you get crystals like this where beryllium is a major constituent when it's so rare? Well, it turns out these form in pegmatites, and pegmatites, as we've learned before, are late-stage magmatic fluids that have formed after extensive amounts of crystal fractionation. And that process results in the progressive enrichment of various incompatible trace elements, beryllium, for example, to levels that they actually saturate their own phases, like this, Beryl. Now, you are probably familiar with Beryl, but may not realize it. When they're pure, they're white, like this, or clear, okay? When they have a little bit of iron in them, they're blue, like this. And this is aquamarine, one that I found in Madagascar. When they have chromium in it, they're green. This is not the prettiest one, and it's not worth anything, but they're green, and we call these emeralds. Emeralds, aquamarine, they all form in sort of similar environments. They need to have a large source of beryllium, except that in the case of emeralds, they also need to have a source of chromium, which is also rare. So these form when pegmatitic fluids or metamorphic fluids interact with ultramafic rocks, which we'll talk about later, which are from the mantle. And when they come together, they precipitate out emerald. There you go.